I think I'll get going. We have like a good amount of people and growing rapidly, so I'll just do a quick introduction. Hello, everyone. Welcome to this month's meetup. Sorry about the initial hiccup. Today we have Frank McSherry, our chief scientist extraordinaire, walking us through the future architecture of Materialize. It's a really exciting time to follow the work that we are doing, in my opinion, as we unravel the existing binary into a fully distributed and cloud-first product. There will be plenty of time for questions, so please drop them in the chat as we move on. If there's a question that is helpful to answer in context, I might nudge Frank straight away, but otherwise I'll try to not interrupt the flow of the presentation. But otherwise, the floor will be open once the presentation is done, so you can just stash all your questions or think about them and then leave them to the end. And Frank will get to them for sure. Cool, Frank, I think you can take it away.
Wonderful, thank you very much. As you'll see as we go through the slides, many of them are discussion points as much as they are piles of content. So we'll get there and I'll try to talk through some of them, but it's a great time to shoot some questions if you have them into the chat. And if everyone has the same question, we should absolutely go through it then. I'll also be around essentially indefinitely afterwards. And we can make sure to shake out all the questions you might have. So Materialize's unbundled architecture. What's this about? So we're gonna set up a little bit of context here, and then I'll get into some details. So Materialize, which many of you may already know, and I'll try to give you a bit of background if you're not already familiar. But for those of you who are familiar with Materialize, you're probably most familiar with it as essentially a single binary that you go and grab and use, and it does a lot of stuff for you. It answers SQL queries really fast against streaming data. But we're moving away from the architecture of a single binary to this architecture that's generally thought of as this unbundled architecture, one where different parts of the binary are popped out and turned into, in our case, it's going to be scale-out architectures for several of these parts, for reasons that I'll get into. Actually, sorry, for reasons that I'll get into right now. So a sane question, say, why you got to do this thing? A single binary is really a pleasant experience when it works, and that's totally true. It's great to deploy and run and stuff like that. It just, sometimes it runs into walls. And these are three that I pulled up as the ones that were most top of mind for me, three themes. I'm sure there are others as well, so I don't want to say that these are limiting, but they're ones that really resonate a lot with folks. One of them fundamentally is scalability. Materialize is, in the big data space, working with people's data that are quite large and change quite frequently. And many users were essentially hitting resource limits. So they would get the largest machine they could find, turn on Materialize, and shove all their data through it with a bunch of complicated views. And if you peg the CPU or the memory in those instances, yeah, you're done, right? There isn't a story for how you can get some more or anything like that. You could turn on a second copy of Materialize next to it, and maybe you could wrangle something that way. But fundamentally, people were looking for the larger use cases, growing the use cases that they already had and expanding out to other use cases, because generally speaking, they like the experience. So we want to support that. We want to make sure that folks don't ever, essentially, as rarely as possible, we have to tell people, no, I'm sorry, you can't have that thing. All right, a second theme was reliability. Okay, with one binary, this is great, again, when everything works, but as it turns out, Materialize is in this fairly interesting space where people are doing new and exciting things. And some of the times the new and exciting things they do cause the system to run out of memory. Or, we'll do an outer join between several terabyte sized data sets, and nothing good happens in that case. And especially nothing good happens if this is the same single process as is running your production use cases. So obliging folks to mix and match their production use cases with their experimental use cases, just no one likes that. It's a bad idea. Everyone is regularly asking, what sort of confidence can I have in my production workloads? And the answers are, well, if you don't touch it, it's going to keep working fine. But we like to get away from that, basically, both reliability and the experimentation and sort of new use cases that are exciting as well. A third thing, which I'm not sure if you see directly as much as a user, but for sure internally and sort of secondhand effect externally, development gets slowed down a bit with the single binary. Initially, a single binary is really easy to put together and roll out, but as the teams grow and the feature sets grow, it's just that much more complicated to keep everything properly in sync without clear boundaries between different parts of the system. And by forcibly decoupling things, it makes a lot of our development efforts more scalable. Essentially, we can add more sources, more types of sources to the system. We can get the query optimization ramped up and decoupled from how we read data and stuff like that. So we'll be able to, we believe, be able to do more total and do things more quickly individually. So some of the reasons, I'm sure there are others as well, but these are among the reasons. So let's talk through just a little bit of Materialize of yesterday. Now, strictly speaking, if you go to the Materialize cloud at the moment, this is what you'd have access to. Though internally, we're already working with the new architecture, so it's a bit tricky to figure out what today means. Materialize of today, what that would be, but for sure, Materialize of yesterday has this bundled architecture. And what I'm going to try to do here is I'm going to just name check a few things. Mostly, we don't really need to think too hard about the picture over there on the right, but I do want to call out stuff that's going on. So just to start with, the outer boundary here, Materialize is, well, yesterday at least, is one process. And it takes in, up in blue there, you can see a bunch of commands, SQL commands that present essentially as if this was a SQL database. You can show up and you can create some tables, you can connect to external sources, create some views, create some indexes, poke around, select data out of things. And fundamentally, it's meant to present very much like a traditional SQL database, except that it is proactively pulling in all of your data from external sources, proactively updating all of the views that you've defined, and trying to make it so that whenever you type select star from my view, we already have the results for you. We don't have to go in and recompute them. So you see also just in the picture data flowing into various places. Fundamentally, what happens in this architecture is your commands lead the SQL layer to put together one of these layers. You can sort of see 3 layers that I built there. Each of these is movement of data from outside the world through this source module, through some data flows. The data flows are the things that will keep up to date your, when you type select, blah, join, blah, group by whatever, that gets turned into a very exotic data flow. And the data ultimately land in arrangements. These are the analog of an index, essentially, an in-memory arranged data structure that allow you to get prompt random access to the current state of affairs. And each of these that you create is a new layer in here. They're independent. They're all sharing the same resources, though you can sort of see I've called out arrangements use a lot of memory. The data flow stuff uses a bunch of CPU. The sources are where we use the network. So it sort of checks out that computers have all of these things. Maybe you could get this to work in just fairly chunky server or something like that. And you can, this will actually work up to a certain point for folks. Now, there's some annoyances. I want to stress before Materialize has a lot of really cool things. So the fact that I'm listing annoyances, it's still, in my experience, a net positive interaction. But let's call out a few things that are poor about this particular architecture. One of them are these shared resources. The fact that we're sharing all of the memory between the different layers in here, sharing all the CPU, the networking even. That is economical when it works, but it does mean that we lack fault isolation, right? So if something goes wrong in any one of these layers, things do go wrong. You may have seen that. Not as many things go wrong as I've been expecting, but when things go wrong, the whole process goes away. Yeah, that's bad. We also lack performance isolation in this model. So if one of those arrangements decides I want to use all the memory, all the memory gets used, and the poor hapless production use case is starved of resources, similar with CPU and network IO as well. Another big problem that you may have noticed is that the data are not durable, right? This architecture is essentially an in-memory architecture where the theory was, back in ye olde times, people love Kafka. They put their data in Kafka and they're so happy with their data in Kafka. They're going to be really excited to have us read their data out of Kafka like everyone does, and we will be essentially a really sweet cache just downstream of that. downstream of that upstream source of truth. Turns out this was not exactly correct. We misunderstood exactly how much people love Kafka. And one of the things that people like is having as few things as possible to manage. So we've been regularly asked, could you just take ownership of the data, please? We would like the data to be durable. I'd like you to pull it into Materialize, and then we'd have Materialize with the data in it and not have to keep that essentially some level synchronized, or keep the data up in Kafka without compacting it away because Materialize might still need it, that type of thing. A consequence of things not being durable meant that anytime there was a failure, if you turn Materialize off and then on again, or even just if you brought up a new data flow, right? If you're reading a source for the first time again, you'd have to pull the data in from the upstream source. That's a lot of strain on these other systems components. You'd also, unless you're using a particular set of sources, you could potentially get consistency glitches. Right? You could read the same data twice and try to do some aggregations, and things wouldn't add up the same way. Super embarrassing. I'm not sure if anyone's actually noticed this, but as a computer scientist, this point of pride that I'm going to fix this, and consistency will be solid throughout Materialize. You might also notice, though it's maybe not as evident without the lived experience, that this is hard to develop for. It's hard to debug. It's hard to attribute failures. It's hard to understand exactly what's gone wrong, and that's annoying. So we're switching away from all of these annoying little warts, and we're going to, as we go forward, look for each of these and see, like, ooh, how are you getting around each of these classes of problem? So here we go. Materialize of tomorrow. This is trialing at the moment internally. We're using it, but in the future, we're going to make sure that everyone has access to this. The architecture is, I'll talk through it. There are three main layers in the architecture. So we're ripping apart that single binary into three core bits of functionality with the names here: adapter, compute, and storage. And you can sort of see visually some hints about what's going to be going on here. The adapter layer is still where the user interacts with the system, presenting again as if it were a traditional SQL database. The compute layer is where all of these data flows live. This is where we do data transformations and implement your join group by logic. And the storage layer is where we pull data in to the system, essentially do ingestion down there. You might notice that I've drawn things in an interesting way with data flow and sources over on the right-hand side of these boxes. We'll get into that in just a moment, why I've drawn the picture that way. But quickly, just building back up, the responsibilities of each of these layers. The storage layer, for example, is going to durably record the source data that flows in and apply durably timestamp each of the updates to your collections. So, if you've pointed us at a Kafka topic or something like that, we're going to be pulling in data. We will be recording the data, timestamping it for reasons that will become clearer in just a moment. But this is essentially taking ownership of the data. So Materialize will now be able to answer all arbitrary questions of yours about the data going forward in the future without having to reconsult upstream sources and without worrying too much about whether those upstream sources have potentially vanished. Just above that, the compute layer is tasked with transforming according to your views and arranging all of these timestamped data. So data that flow out of storage, but also timestamped data that flow out of the compute layer. They can stack, you can stack views up and transform data that have already been transformed. But the compute layer is manipulating all of the data, turning it from one representation into another through a bunch of complicated SQL stuff that you've described. And then finally, the adapter layer up here has the interesting job of translating the commands that you give it, these SQL commands, into timestamped actions. And might be fair to scratch your head and say, what's that about? Fundamentally, what this means is that things like select and insert, these sort of commands that data manipulation commands that you introduce, are also going to be timestamped the exact same way that the underlying changing data are timestamped. And this is, in a sense, how we provide consistency throughout the system. Now, you may notice we said timestamp a lot. And this is a pretty important concept here in terms of decoupling these components. Right? The hard thing about breaking components apart in systems generally is that When they were coupled, you could get their behaviors to be nicely lined up so that you could have some guarantees about what they're going to go and do. And it's a little harder as you start to rip things apart to make sure that you're actually getting a sane system that sort of end-to-end things still make sense. The mechanism that Materialize is using for this is called virtual time. There's a great paper to go and read from the 1980s about this, but fundamentally it means write the time down next to the data. Anytime something changes, write a time down next to it. These times become the source of truth for when a thing happened. May not have literally happened according to your watch at that moment, but that's now the source of truth. That's when it did happen. And when you show up and do a select of a particular query, we'll find a time to associate with your select, and we will give you the correct answer exactly at that virtual time. So these times end up as the decoupling mechanism throughout these different layers. As long as we can correctly respect all of the times that have been announced by the storage layer, properly respected by the compute layer as it transforms the data, and then presented up to the adapter layer who picks out the answers at specific times, all of the layers can collaborate together effectively without tying on their tangled shoelaces and falling over and giving incorrect answers. All right, so we'll barge forward just a little bit now into a little bit of discussion of each of the layers. I'm going to try to call out some of the cool properties that each of them have. All right, starting with storage. So this is storage. We saw that picture up there. Primary function of storage is to record each of the event streams that come in as a durable time-stamped history. We're going to be recording them off to S3. So this is great news. It's elastic, scalable, economical, sort of a good place to be putting data. It's also great news that we're not inventing our own new storage infrastructure. So this is where we're going to be pulling data in, writing things down, and acting as the source of truth for Materialize and your uses of this data through Materialize. There's some cool new properties here. First of all, you can see all the sources that I've drawn vertically. Each of these are potentially schedulable in their own independent pods. They're independent, right? The assignment of timestamps to updates and the transcription of these updates into S3, independent. So they can be deployed out in their own Kubernetes pods. The scaling here is essentially limitless. You can start to use as many sources as you want, as long as you have the compute resources for them, which we'll happily arrange as you need them. Moreover, because of the wonders of virtual time, the users of these sources are very nicely decoupled from the source transcribers. They're going sort of rendezvousing by way of S3 and by way of these virtual times. So they can proceed largely without coordination. I mean, the compute layer, for example, can't proceed at a time until the data are actually available, but they don't need to be in close coordination with the actual storage processes that are doing work, unlike how Materialize used to be. So the sources can, for example, fail, turn off, turn on again. The only thing that'll happen is that the other layers who are trying to read the data will stall for a little bit while the presented data aren't yet available. So the isolation gives us some nice characteristics in terms of reliability, in terms of scaling. That's great. The durability is also really exciting. This is a fundamentally new feature for Materialize, which used to be a non-durable, essentially in-memory, very fancy cache. But by making things durable, we have a lot of new opportunities. One of them that's great is you type create source, semicolon, press enter, with a lot more text, to be honest. But you type your create source command, press enter. We will start ingesting it right then. This is distinct from how Materialize has historically worked. We will wait for you to actually go and use the data. We'll actually just start pulling this in right now so that when you actually do need to use the data, the latency is dramatically reduced, right? So we won't have to start the pulling of the data when you finally issue your view. The data will all be ready on hand and good to go. Moreover, finally, we're able to, using our own persistence layer, maintain a compacted representation of this data. So if you've had data that you've been collecting for months, it's churning pretty regularly. We have no interest in the history going back months. You may have no interest in that history, sorry. And if not, we're able to compact the data in place, keep your footprint substantially smaller so that when you have a new query, we just hydrate it with the compacted representation rather than a history that goes back much further than you're actually interested in investigating. And this is possible only because we've taken some ownership over the persistence layer. This is not something that Kafka would give you So it's good that we're taking some ownership and doing the right data representation for our internal data model. Great. So this is what storage does: makes create source immediately responsive and scalable. You can type create source as many times as you want and keep pressing up enter, you just get a lot of sources. And the only thing that'll happen is S3 will start to fill up. Nothing will fall over, we hope. All right, the compute layer. Compute layer lives just above the storage layer. It transforms and arranges these timestamped histories. And one of the things, just to call this out immediately before I forget, one of the important characteristics of the separation between compute and storage is to have the property of the separation of compute and storage. This is something that's been demonstrated to be super popular in the data warehousing space, where you're allowed to scale out your storage and scale out your compute independently. If a new person shows up and wants to use some new compute, we don't have to give you a new Materialize instance. You can just add on the resources here at the compute layer. Maybe getting a bit ahead of my health, sorry, but otherwise I could forget to mention that. Right, in the compute layer, there's one new concept, and this new concept, most of Materialize has stayed the same with this re-architecture in terms of the concepts presented externally, but there's a new concept here that users are going to want to be aware of. And these are the concept of a compute cluster, where a compute cluster is essentially a little virtual Materialize instance, where the compute aspect of a Materialize instance that you can turn on. It'll have some compute resources backing it, and you can start to install data flows, build indexes, select data out of these clusters, just in a sense, just as if you were using Materialize of yesterday. But you can have many of them. This is sort of the cool thing. You can have a production cluster that will be totally isolated from other clusters that you go and install. So you can have a production cluster, demo cluster, 5 intern clusters, all these sorts of things, and they will not compete with each other for resources. The only interactions they'll have essentially is through the storage layer, where they'll both be pulling data out of the same data sources. So you'll be able to get consistent results across each of these clusters. Though CPU, memory, things like that, they won't compete with each other. If one of them catches on fire and crashes, that's too bad, of course, but the production cluster will not catch on fire and crash just because one of the intern clusters did. So it's an interesting concept to expose. It is still valuable. We could have sharded each of the data flows out into their own pods and own isolated resources. So if you're facile with Materialize, if you've used some advanced concepts there, you understand that index sharing within and across data flows is valuable. So the cluster is sort of this quantum of sharing. Anything that you put into a cluster will be shared within the cluster, but we have fairly hard isolation between the clusters. All right, one really cool thing, I think it's really cool, that comes with our new architecture, where we take ownership of the data and record durable timestamps in the storage layer, is that the compute layer, all of these transformations we're doing are deterministic. And your view, join, group by, what have you, has a correct answer, and at every moment in time it has a correct answer. And so we can actually turn on, for each query that you've expressed, we can turn on multiple compute instances behind it. So we can replicate, in particular it's called active replication, the compute resources behind your cluster, to keep the low latencies, the uninterrupted behavior, even in the presence of a whole bunch of random quirks that you might experience. So if machines crash randomly or get migrated around, this provides fault tolerance in the sense that as long as at least one of your cluster replicas is up and running, you will still have uninterrupted access to your data. You can literally, in Materialize of tomorrow, turn on a tail and watch results flow back in sort of sub-second latencies. Go and turn off one of the machines participating in the cluster, and you don't notice anything. It's the cutover from one to the other is immediate. It allows you to do some really fun things. So we put on here 0 downtime rescaling. So if you're working on a test project, let's say you just picked a small instance size because that's all you think you need for starting out. You eventually realize this is really cool, but the data is growing. Let me turn on a much larger instance size as a new replica. As long as you wait for it to reach parity with the smaller replica, you can then just go and turn off the smaller replica, and it'll cut over seamlessly to the new replica. So you can migrate around the resources that you've backed each of these clusters with, essentially with no observed interruption to their execution. And in the future, though not immediately, but in the future, version upgrades are meant to work exactly the same way. So as Materialize goes through various version upgrades, no particular reason to force you to stop any of your computation. We just sort of slot in a new replica with a slightly advanced version, wait for it to catch up, do any reconciliation that's required, and then cut over to the new one. As an exciting bonus, horizontal scaling will be turned on finally. Horizontal scaling has been there forever in Materialize. It turns out we've just been very hesitant to deploy it in the single binary case where we don't have fault isolation, right? So if the more computers you involve in something, the more likely it is to catch on fire. But now that we have isolation between the compute clusters, folks are much more comfortable allowing us to turn on horizontal scaling. So if what you need is a 64 computer timely data flow installation, great. We're happy to give you that. And it may catch on fire. We'll see. It's much easier to catch it on fire than just a small teensy little instance. But it's now available. Alrighty. So the last layer to say something about is the adapter layer. This is where the SQL commands come in, and the adapter layer is what presents, essentially, it adapts your commands into interactions with the compute and storage layer to provide the experience of a SQL system. Now, a lot of the work that goes into here is parsing SQL and optimizing your queries and things like that. But when you get down to the heart of it, like its interface with the rest of the system, its job is to translate the commands that you've expressed into timestamped actions. What this does is a bit of a rendezvous between your commands and the changing data, right? And we want to do this rendezvous in a way that gives you unsurprising answers, hopefully the types of answers you want to see, but is able to provide consistency properties. So rather than just giving you random answers or answers that were accurate as of 20 minutes ago or something like that, we have the ability to give you very specific answers that have very specific freshness and consistency properties. So just to reiterate, commands like select and insert get timestamp, and they happen exactly at the moment of the timestamp. Once the timestamp is determined for these commands, there is a correct answer to produce, and we provide that correct answer to you. The reason that this is exciting is that we can use these virtual timestamps to provide consistency properties you typically see in OLTP style databases. So these are properties like serializability, which you get almost for free. The virtual timestamps themselves, if you're familiar with serializability, it requires that all of the events in the system have happened in some total order. The timestamps are essentially that order, and we can more or less ensure that your interactions with Materialize will satisfy the database property of serializability. If we do a little bit of additional care, we can actually get to strict serializability, and this is really nice. This is essentially as good as it gets from a database consistency point of view. There's actually a few little bonus things we can add on here that we'll see as sort of stretch goals for the upcoming months, where we can actually provide strict serializability with respect to external sources as well. So you do an insert into your Postgres instance, head over to Materialize, select, and you'll see the results, guaranteed. We'll see if we make that. The mechanisms exist and are totally sane, and it's a question of time. But yeah, the adapter layer is now, I would say, much more principled, or has a foundation to be much more principled about how it provides strong database level consistency guarantees, ones that make it much more sane for you to think about using the system to build data applications, things that are actually intending to interact with the system, Materialize, and see a natural progression of things. If you go and you insert some data, you come back, you select, you really hope to see it, and are super surprised if you're using a tool that doesn't provide that property. So, great. The more it gives the lived experience, the ergonomics, if you will, of a database and the performance of a scale out stream processor, the happier we are. All right, so I'm just going to wrap up, and we can sort of shift over to various question askings and answerings. So just to recap, Materialize up tomorrow. So first of all, there's a shameless plug. If you're interested, you should absolutely head over to materialize.com and sign up for a hands-on demo. We're happily handing these out, showing you what this actually looks like now, today, and you can hop in the queue for early access as well. Just to reiterate these sort of key properties, the new features that are coming out with each of these layers. Storage is managing durability for you through S3. It's scalable, elastic, cheap, so it's a sane place to put your data. Compute has all sorts of new exciting scaling properties. It can scale out isolated use cases as you like. It can do horizontal scaling, a bit better now. And active replication gives you, basically uses scaling to give you higher availability, reliability. And nicely decoupled from storage so that, if a new user shows up and says, hey, I'd really like some of whatever you're doing with Materialize, you just add a new cluster for them, they're good to go. They don't need a new copy of Materialize or a new copy of all the data or anything like that. And finally, up at the adapter layer, strong consistency, still with low latency. So all of the power of one of these scale out systems with essentially the strongest of database consistency guarantees. And that's all I have for you. I'm going to leave this up because it may be helpful in terms of talking through. You might have noticed that there's really just one figure in the whole talk, but talking through different parts of the new architecture, I can well, I guess I can't really point at the screen, but it may be helpful.